In this paper, we present a compressive light field camera architecture that allows for high-resolution light fields to be captured in a single image. For this purpose, we explore the co-design of optimized optical coding strategies and compressive computational processing. As shown in this example, a 4D light field can be recovered from a single coded sensor image. Parallax is observed even for complex lighting effects such as occlusion, specularity, and refraction being exhibited by the background, dragon, and tiger, respectively. Current technology trends include single-shot approaches that multiplex a low-resolution light field into a sensor image, for instance using lenslet arrays or coded masks. Alternatively, high-resolution light fields can be acquired in multiple images using camera gantries or coded apertures. Unfortunately, such approach makes it difficult to capture dynamic scenes. Camera arrays can be employed to overcome this limit, but are expensive and usually bulky. We give 3 key insights into both optical and computational camera design parameters. First, the fundamental building blocks of natural light fields, light field atoms, can be captured in dictionaries that represent such high-dimensional signals more sparsely than previous representations. Second, this sparsity is directly exploited by nonlinear sparse coding techniques that allow high-resolution light fields to be reconstructed from a single coded projection. Third, the optical system can be optimized by preserving the information content of the light field atoms. We propose to learn light field atoms from light field training sets. For this purpose, a large number of small 4D patches is extracted from the training set. Sparse coding techniques are employed to learn an overcomplete dictionary that contains the essential building blocks or atoms of the training light fields. These atoms capture high-dimensional edges as well as high-frequency structures exhibiting different amounts of rotation and shear. To build an intuition, we extract a single 4D patch from a light field. Here we show a single color channel of the test patch and represent it with 12 light field atoms. We observe that even a few atoms faithfully represent the target light field patch. In the proposed camera design, a coded 2D projection of the 4D light field is recorded. Recovering the light field requires a system of equation to be inverted as illustrated here. The most critical aspects of robust reconstructions are optimized optical projections and sparse representations of the light field. Sparsity, exploiting reconstruction algorithms, are employed to recover the light field. We explore all of these aspects in detail in the paper. To verify our mathematical framework, we build a prototype compressive light field camera. This setup emulates a camera that has a coded attenuation mask mounted at a slight offset in front of the sensor. In our prototype, we use a single lens reflex camera together with relay optics and a reflective LCOS display in the optical path. The camera is focused in front of the LCOS, placing a virtual sensor behind it and therefore emulates the desired mask-based setup. We can capture training light fields in multiple camera images by displaying shifting pinholes on the LCOS or capture coded projections by taking a single photograph while showing an optimized pattern on the LCOS. In the following, we show results that are reconstructed from a single coded projection captured with our camera prototype. The same dictionary and optimized mask pattern is used for all of them. This is a set of cards located at different distances to the camera's focal plane. A 4D light field with 5x5 views is reconstructed. By shearing the 4D light field and averaging views, we can synthetically refocus on the foreground and background. This scene exhibits occlusion by a high-frequency shrub. partially occluded areas such as the toy's eye are faithfully reconstructed. The proposed algorithms allow a 4D light field to be reconstructed from a single sensor image. Dynamic events, such as this rotating carousel, can be recovered. We show reconstructions for several frames of an animated sequence, parallax observed in all of them. Slight angular changes in color and intensity are introduced by the prototype setup. We evaluate the proposed techniques for synthetic scenes and compare previously used broadband codes, random mask patterns, and optimized patterns. Optimized optical codes, as derived in our paper, allow sharp features and great parallax to be recovered, even from a single shot. In our paper, we also analyze the depth of field of the proposed system and evaluate a range of existing light field cameras. We show additional applications such as 4D light field compression and denoising for the proposed dictionaries. Please refer to the paper for more details.